Good afternoon, honorable chief guests, respected teachers, and one and all present here. A very warm welcome to you all. My name is Shivani Thakur, student of MSc first year same 2. Today, I am delivering a seminar on the topic of cycloaddition reaction. Here is the outline of my presentation, which will I explain briefly one by one. Before moving towards our main topic, I will explain from where the cycloaddition reaction is taken, that is pericyclic reaction. Pericyclic reaction, all such concentrated reaction which proceed via cyclic transition state, and the transition state is formed there is totally unstable and it is spectroscopically not detectable, while in pericyclic reactivity can be understood in terms of the frontal molecular orbital, that is HOMO and LUMO, and the outcome of this reaction is totally a cyclic product. More about the pericyclic reaction are completely stereospecific in nature. In pericyclic reaction, most of the reaction as take place at the periphery of the ring. Now, the properties of the pericyclic reaction. In the pericyclic reaction, there is no formation of any intermediate. There is no requirement of any reagent to initiate the pericyclic reaction, while the pericyclic reaction are the independent on the nature of the solvent and the nature of the catalyst. In the pericyclic reaction, there is no involvement in electrophile or the nucleophile. Now look at another aspect, the classification of the pericyclic reaction. The pericyclic reaction are classified into four types. First one is the electrocyclic reaction. In this type of reaction, the intramolecular cyclization of conjugated polyenes takes place under the thermal and photochemical condition, which gives the cyclic product. While second one is the cycloaddition reaction, the reaction in which two unsaturated combine react and forming a one cyclic product. While third one is the sigmatropic reaction, it involves a migration of a sigma bond within the pi bond formation. Fourth one is the group transfer reaction, it involves the migration of a group from one species to another. Now let us move towards our main topic, that is cycloaddition reaction. The cycloaddition reaction are the reaction in which two unsaturated compound form a cyclic compound by a concentrated way, that is bond making and bond breaking takes place simultaneously and the cyclic product is formed. It sometimes the cycloaddition reaction may be reversed, then it is called as the reverse cycloaddition reaction. In cycloaddition reaction, there is a formation of a 2 sigma bond by consuming a 2 pi bond. While cycloaddition reaction may be of two types, first one is the intermolecular and second one is the intramolecular. In intermolecular, the reaction takes place between two molecules, then it is called as the intermolecular cycloaddition reaction, while if the reaction takes place within the molecule, then it is called as the intramolecular cycloaddition reaction. Now we will learn the two terminology which will be used for the derivation of Woodward-Hoffmann selection rule for the cycloaddition reaction. First one is the suprafacial bond formation. For the cycloaddition reaction to occur, the HOMO of one reactant should be react with the LUMO of other. That is, if we show in the diagram, the positive terminal of one reactant should be interact with the positive terminal of the other reactant. So such a bonding interaction is called as the suprafacial bond formation, or mainly called as the supra, or mainly called as the supra. While second one is the antifacial bond formation. For the cycloaddition to occur, the positive lobe of one reactant should be interact with the negative lobe of the another reactant, or the lobes of same phase should be interact with the lobes of opposite phase. Then the bonding interaction occur is the antifacial bond formation, or more simply it is called as the anthra. Now, the classification of the cycloaddition reaction based on the number of pi electron of the reacting species is mainly divided into two types. First one is the 2 plus 2 cycloaddition reaction, while second one is the 4 plus 2 cycloaddition reaction, which will be explained by me one by one. First one is the 2 plus 2 cycloaddition reaction, in which the conversion of two molecules leads to a cyclobutane as a product, in which two pi electron system react and forming a cyclobutane or the cyclo product. As we know, the Huckel molecular orbital rule, the molecular orbital are present in ethylene. There are two. First one is the psi 1 and second one is the psi 2. As the 2 pi electron are present in ethylene, so the 2 pi electron are occupied in the psi 1. The psi 1 act as a HOMO, while the psi 2 remain unoccupied, so psi 2 act as a LUMO. If we derive the Woodward-Hofmann's rule for this 2 plus 2 cycloaddition reaction under the thermal condition, in this, as we know, there are two types of molecular orbital are present in ethylene, psi 1 and psi 2. In this, the psi 1 is act as a HOMO, while the psi 2 act as a LUMO. So here is the HOMO of ethylene, HOMO of one ethylene molecule combined with the LUMO of other. Since the HOMO and the LUMO having the two different symmetry, that is positive and a negative, so the allowed bonding formation is antifacial. But it is not possible due to the small size of the cyclobutane. So the 2 plus 2 cycloaddition reaction is thermally not allowed in 2 plus 2 cycloaddition reaction. While under the photochemical condition, the symmetry of homo-excited ethylene molecule is same as the LUMO of ground state molecule of ethylene. So the bond formation takes place here is suprafacial. So the 2 plus 2 cycloaddition reaction is photochemically allowed in 2 plus 2 cycloaddition reaction. Now, the second one is the 4 plus 2 cycloaddition reaction. In this, one of the best example of the 4 plus 2 cycloaddition reaction is diol-Alder reaction, in which 1,3-butadiene react with the ethylene forming a cyclohexane as a product. That is, 4 pi electron system is react with the 2 pi electron system forming a product. While as we know the Huckel molecular orbital, there are two types of molecular orbital are present in the ethylene. That is, first one is the psi 1 and second one is the psi 2. As the 2 electron are present in ethylene, so the 2 electron are occupied in psi 1, so psi 1 act as a HOMO, while the psi 2 remain unoccupied, so psi 2 act as a LUMO. While in 1,3-butadiene, there are four types of molecular orbital are present: psi 1, psi 2, psi 3 and psi 4. In 1,3-butadiene, the 4 pi electron are present, which will occupy the psi 1 and psi 2. So psi 2 act as a HOMO, while the psi 3 remain unoccupied. So in ground state, the psi 3 act as a LUMO. While in the excited state, one of the electron from the psi 2 it jump to the psi 3. So psi 3 act as a HOMO in the excited state, while the psi 4 act as a LUMO. As we consider the Woodward-Hofmann rules for the 4 plus 2 cycloaddition reaction as same as the 2 plus 2 cycloaddition reaction, in 4 plus 2 cycloaddition reaction under the thermal condition, the same symmetry is found. So therefore there is a suprafacial bond formation takes place, while under the photochemical condition there is a, due to presence of a different symmetry, there is a formation of a antifacial bond formation. From the above data, we can summarize the Woodward-Hofmann selection rule for the cycloaddition reaction. If the number of pi electrons of both the reactant taking part reaction is 4n, then under the thermal condition, the allowed mode of formation is antifacial, while under the photochemical condition, the allowed mode of formation is suprafacial. While the number of pi electrons of both the reactant taking part in reaction is 4n plus 2, then under the thermal condition, it may be suprafacial, or under the photochemical condition, it may be antifacial. Now moving towards our another aspect, that is application of cycloaddition reaction. Cycloaddition reaction are the most useful pericyclic reaction in the organic synthesis. Application of cycloaddition reaction will be used in the material science field, are very innovative structure and architecture with several promising application in biological energy and optical devices. One of the best recent application of cycloaddition reaction is as in graphene, fluorine and carbon nanotubes can be easily functionalized by the cycloaddition reaction. Also in solid state organic solvent to check the solubility. While the third one application is the electronic and optoelectronic material devices. Here is the references of my seminar topic. Thank you so much for watching me. Here is end of my seminar topic. Here is end of my seminar topic. If you have any question, then I will happy to answer them. Thank you.